Okay, I should be live. Here's the thing, guys. Um, I am apologize for being a little bit late today. I just woke up right at 5 o'clock. There isn't very much I can do when I wake up at 5. It takes exactly, well, roughly 10 minutes for me to get ready. Apparently today it took exactly 10 minutes. Some days it takes longer, some days it takes a little bit less. Usually I try to get up at 4:30 for these streams, but unfortunately, I don't know, something happened last night and I just couldn't get to sleep until about midnight, so I don't know, it's whatever, that's just what happened. Anyway, let's go ahead and get started with what we're going to work on today. It is going to be a continuation of what we worked on yesterday, as are pretty much all of my streams, unless I'm starting a new simulation. Turn down the music on my end, and let's go ahead and get started. So let me first... Oh, wait a minute. I need to get something real quick. I'll be back in 2 seconds. I apologize for starting and then leaving and then starting again. 1 second. Notebook. Me and my notebook. And let me check real quick to make sure I am live before continuing. I don't want to accidentally start and then have to start again just like I just did. So let me check. Looks like I'm live. Everything should be good to go. Okay, so what are we doing? Well, right now we're working on the algorithm that you guys know and love that we've been working on for the past couple days. The Barnes Hut algorithm. Here. Barnes Hut. Okay, so the Barnes Hut algorithm, again, we've discussed this before, is basically a way for us to do what's known as an n-body simulation, which basically means as many particles as we want. 1 second, particles as we want. Okay, so what does that mean? Well, it means that we use some sort of trick, this time half numerical, half physical, in order to allow us to use more particles than we typically could in an ordinary simulation. What do I mean by that? I mean that our computer is limited in space for a number of reasons. You know, we've got a limited amount of memory, we've got a limited amount of processing power, and if we did millions upon millions of particles without using some sort of numerical trick, well, it'd take, well, a long time to run. Here, it takes significantly less time to run. In fact, if we talk about scaling, if we just, let's say we put a whole bunch of particles in a box. And let's say that all these particles are influencing each other with some sort of force that we'll call the gravitational force. The gravitational force, of course, is F equals big G, mass of one, mass of the other, over R squared. Okay, so let's say we're all influenced by this one force here. Okay, now, this means that we, in order to find what forces are affecting, let's say this particle here, we have to take into account the force of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, so on and so forth, like 35 particles, however many I drew here. Not sure how many I drew, just saying 35. And that's kind of a pain. So then, in order to calculate the next one, we have to calculate 35 more forces, and 35 more forces. So it's going to be 35 times 35, or n squared. However, with the Barnes Hut algorithm, this drops down to n log n, for which we could discuss, or we could just kind of say that's a thing. Now, new page before. How does it work? Well, let's say we have, again, another box. And in this box we have a number of particles. I'm just going to draw them like this. Something like so. Okay. What we do is we first create something known as an octree. 1 second. And this is for three-dimensional systems. However, in two-dimensional systems, it's known as a quad tree. And you'll see why in just a second. That was meant to be an E. 2D. Okay. So what we do is we first split the system down the middle, exactly in half. Then we split it in half again over here. Okay? We split it in half again, half again, half again, half again. Here we split it here, and there, and there, and there. Good. We'll say this is in that box up here. Half, half. Looks good. Half, 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 half. 1 second. Half. Oh, this is going to be a bit of a pain. Oh, no, that was okay. Then we do this, that. Okay? So what we've done is we've continually split the space into segments of 4 until every single box is either completely occupied by one particle or not occupied at all. In this way, we've created a tree, and again, this tree is kind of hard to draw, but the idea is that we have a huge box to start, and this is our root node, the big box on the outside. So this guy right here, which I'll kind of put in red, I guess. This guy. Hey, I care. Right here is our big exterior box. 1 second. And this is our root node. Then we have 4 interior boxes. Right here. 1, 2, 3, 4. So this goes to 1, 2, 3, 4. And forgive me, I'm not very good at drawing this tree. Then each of these guys split up even further. So we'll do, I don't know, green here. So splits up here, and there, here, and there, here, and there, here, and there. All of them split up. So we have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Good. And then some of these guys split up, which I guess we'll put in bright blue over here. So here, there, here, there, here, there, here, there. Almost done. And of course, there. Okay. So then if we were to draw these, we'd say, okay, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Pretend this is a well-drawn tree, guys. It's not, but, you know, use your imagination. Let me see. Actually, and I just did that wrong anyway. This freaking, I don't know what I'm doing with my life. Okay, so this guy does 1, 2, 3, 4. And then this guy has 3. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Something like this. So of all these nodes, it looks something like this. So we have a whole bunch of nodes where every particle is now associated with one node. Now, we give all of these nodes a couple of different conditions. We'll say the node has, let's say, particles, which we've put into a large vector, which is pvec, particle vector. Then it's got, let's see, I'll put in particle here. Then what else does it have? Well, it's got a center of mass. And each of these particles has an acceleration, a velocity, a position, exactly as you might expect, a mass, and a radius. Okay. And then this points to all of the children node. In the case of an octree, times 8. And the parent node, which is just 1. And this is basically what we've got in order to work with our system here. So let me think. Good, that should be good to go from there. Now, what are we doing today? Well, as of now, we've officially implemented our octree. I'm quite happy with how far we've gotten there. Now, we have to implement the next step, which is the force integration. I don't know how long this will take. We'll see what happens. But I'm pretty sure it'll take most of the day. At least writing it up and testing it together should take most of the day. If we need to, we'll take some of tomorrow too. But in essence, this isn't so big of a deal, right? We're going to be implementing the Runge-Kutta method. Runge, I think spelled like this, Kutta 4, which I just call RK4. It's a super common, I guess, force integration method for this kind of stuff. It's used especially in video games, but it's also used a good bit in research of some sorts. At least I used it in my previous molecular dynamics research. So it's kind of nice to have. Let me think. The last time we did MD, we did a super simple form of MD. Sorry for yawn. Where we just assumed the only type of collisions we have are, well, collisions where people run right into each other, right? Here we're assuming that instead of those types of collisions, we have the gravitational force law, which is equal to GMM over R squared. Hey, Rory Richards, what's up? So in this case, we would expect, let's say, a particle here, and we'd see some sort of orbiting or something like that around other particles. Or we could see the particles directly impact each other, but the idea is that we do see the forces acting on each other. Now, of course, there's a whole bunch of things we can do with this. Because we're going to be using OpenGL to visualize it in a bit, we might actually have a good case to turn this into a small little game just for fun, you know? I won't spend more than a week or maybe 2 weeks on it, but it might be a good exercise to turn it into a game in the end. And of course, with my feedback forums, which I do read a good bit, you know, I check every couple weeks or something like that. With those, a lot of people said that they'd like to do some form of game development, so maybe we should try it. Because I'm actually super interested in the idea of having video games that are related to some very heavily scientific content. Just because it's done sometimes, but not very frequently, and I think it can be a lot of fun. So not necessarily like a learning game, you know, I don't want people to necessarily like go to the game to learn how to use an algorithm, but if it's heavily based off an algorithm, then they'll get an intuitive feel for how the algorithm works without necessarily knowing that they're learning, right? And that's the idea, to manipulate people into learning. Good, okay. So RK4, how does it work? Here's the idea. New page before. We are going to basically keep track of all the particles' position, which is going to be equal to the velocity times time, plus x naught. Velocity, which is going to be equal to acceleration times time, plus x naught. And the acceleration, which is going to be equal to a sum of all of the, hey Gustorn, let's say mass I, FGMM, times the gravitational constant out front over r squared. Okay, so that's kind of how we're going to keep track of everything. We've already kind of sort of got the acceleration down, so now it's a matter of going backwards to find the velocity. Yep, should be v naught. Sorry about that. And then going backwards to find the position. Good. So that's kind of the idea that we're going to be doing. How do we go from one to the other? Well, we use the Runge-Kutta method. Now, the Runge-Kutta method, again, I've been saying that word a lot. Let me just go ahead and explain kind of sort of what we're doing here. I'm going to take out some notes just to make sure that I'm not saying something incredibly stupid here. But in essence, it's not so bad, right? Because we know that the position at any given point is equal to velocity times time plus some sort of original position. And we know that the velocity at any given point in time is the acceleration times time. Let's see, 1 second. With some sort... 1 second. With some sort of initial velocity, we can kind of work from there. So in the end, here's kind of what we're trying to do. We're trying to find the position, which is going to be equal to, here's how I'm going to write it. It's going to be x naught plus 1 over 6 times v1 plus 2v2 plus 2v3 plus v4. And we'll say v is going to be equal to v naught plus 1 over 6 times a1 plus 2a2 plus 2a3 plus a4. Okay? So, what do we have here? Well, basically what we're going to do is, remember how I said that the acceleration is going to be equal to a sum of all of these changing positions? We're going to kind of go back and forth between changing the position and acceleration here. So we recalculate the acceleration and the position. This is going to be mighty slow the first time we do it, but we're going to try to find ways to speed it up. Okay, so here's how we're going to do it. We have to find the different V's and the different A's to find the different P's. So to find the different velocities and accelerations, we kind of need to do them all at once, right? So here's what we'll do. New page before. We're going to say x1 is going to be equal to x naught, okay? v1 is going to be equal to v naught, and then a1 is going to be equal to... Yeah, I did. Well, okay, it depends on how you do it. You could put the time operator in here. Oops, 1 second. I meant to do this. But you're right, there should be an H or a time step or a DT. We'll put a DT out here. Totally right, I need the time operator. Okay. Up here. So, then we're going to say A is going to be equal to GMM over R naught, or x naught, rather. Okay, then we're going to say x2 is going to be equal to x plus 0.5 times v1 times dt. Okay, so that's why I kind of left off. Oh, no, this should be good. Okay, v2 is going to be equal to v plus, these are all knots, 1 second, plus 0.5 times a1 times dt. Okay, and then a2 is going to be equal to g m over x1 squared. Okay, and you can kind of see how this continues into x. That was meant to be a straight line, and it was anything but straight. That's a little bit closer. Let's say x3 is going to be equal to, actually, let me draw it over here. x3 is going to be equal to x naught plus 0.5 times v2 times dt. v3 is going to be equal to v naught plus 0.5 times a2 dt. And then a3 is going to be equal to g m over x2 squared. Okay, and then finally x4 is going to be equal to x naught plus, this time no 0.5, it's just going to be v3 times dt. v4 is going to be equal to v naught plus a3 times dt, and a4 is going to be equal to g m over r3 squared. And I mixed up my r's and x's, my apologies. Let me go back to the last screen. Good, okay, everything should be right. Okay, now, after we calculate all of these guys, again, finding the position, finding the, 1 second. Finding the position, finding the velocity, and finding the, 1 second. Acceleration is not very hard. The acceleration is, well, what you would expect, just gmm over r, so I'm not going to worry about the acceleration here. But the velocity is going to be equal to whatever it was to begin with, v naught plus dt over 6 times v1, I'm sorry, a1 plus 2a2 plus 2a3 plus a4. Okay, same thing over here, x naught plus dt over 6 a v1 plus 2v2 plus 2v3 plus v4. Okay, now a couple things to note. In the end, just to do a very quick unit analysis here, again, position is equal to velocity times time. So we have a position here and we have a velocity times time. Velocity is equal to acceleration times time. So acceleration times time with some sort of initial velocity to start. So we know the units check out. Now, what else do I need to say here? The other thing to say is that V2 and V3, if we go back to those formulas, we're both multiplied by 0.5 here and here. So it kind of makes sense that they have their values multiplied by 2 again when we go through here, and then we divide by 6. So we have 1 unit, 3 units, 5 units, 6 units. 1 plus 2 plus 2 point plus 1, so that makes a total of 6. We divide by 6. So it's kind of in a way like we're averaging them and we're adding them to x naught, in a way. You might not be able to see all that v equation, so I guess I'll just go to the other one that I drew over here. Wait, here. Okay, so that's kind of where we're heading. We'll see how far we get. We'll see if it works. It might break, in which case there are a couple things I want to check because maybe I got a couple equations wrong, but we'll kind of go through there. This is what I'm currently thinking, how it should currently work. So, let me go ahead and turn on my air conditioning, get a quick sip of water, and then we can go ahead and get started. Again, let me know if you have any questions. It should be okay. Oops, sorry about that. I totally just hit my microphone. Hopefully it wasn't that loud. Okay, good to go. So, let me go ahead and pop this over here. Pop that over there. It's okay, I love Twitch. I'm glad you came in anyway. I realize It's probably super late your time if you're in Europe. And honestly, a lot of the people who watch are from Europe. So, I would guess it's kind of late. So if you have to leave early, I totally understand. Don't worry about that. So let's go ahead and cd into projects, Simulaos, and of course Barnes Hut, which is the algorithm we're working with. Cd into projects, Simulaos, and of course Barnes Hut. Now yesterday we made a makefile. Let me just go ahead and run the makefile just to make sure it works. Good, seems to work okay. Now let me run the last new plot command to show you guys the octree that we have so far. This is what I was discussing at the very start of the stream just a few minutes ago. It's kind of exactly what you would expect. And again, we can kind of create some sort of, how do I put that? We can create some sort of, wait, I have to think about how I want to phrase this. So here's what's happening. It's split here, it's split there, it's split here. I'm sorry, here and there, here and there, here and there, if that makes sense. So you can kind of see how it's split across the way. Now, what am I trying to say? One second, I have to think about that. I'm trying to say we can create basically a method that allows us to check which nodes we have to check forces against, right? So that's how we work on. This is not Blender or OpenGL. This is actually just NuPlot. It is a plotting software that a lot of people use. I use quite frequently when I just need to do something quick. And I have the ability to output data files. When I don't have the ability to output data files, then I'm screwed because there aren't very many ways for me to do that with my current setup. So, okay. NuPlot's quite nice for a lot of things, actually. Okay, so now let's go ahead and get into the code. So VI, Barnes Hut. Oh, that was the wrong file. That's CPP. Okay, so that's our octree. Yesterday we spent a good bit of time working on this function that we called force integrate. Now, how far did we get? Well, we didn't get so far, but that's okay. So let me go down to the bottom. What we implemented is this rksearch function. The rksearch goes through and basically says, hey, look, we are interacting with this particular set of nodes in this particular way. Again, what we're going to do is we're going to say, well, we only have to deal with an internal node, so we don't have to deal with exact particles if we're sufficiently far away, which means we're basically clumping particles together. If we are, very, very far away, or the clump of particles is incredibly close. This way, basically those particles act as a single particle instead of multiple particles, cuts down a little bit on compute time. Okay, so now we have to do the RK4. Well, let me go real quick up to, one second, Control D, VI Barnes Hut.h, and let me check the particle class. So in the particle class, we have position, acceleration, and velocity, mass, and radius. Okay, so what do we need to do? We need to basically go through and update them in exactly the same way that I just said. So, what do we have here? We have a simple vec velocity, vec acceleration. So this means it is a x, y, and z. So we'll have a position, an acceleration, and a velocity all in x, y, and z Cartesian coordinates. So what are we going to do? Let's do it. So for RK4, we need a vector of, I guess, vectors for v, let's see, acceleration, velocity, and position, which will then be added together in the end. So let's do it. So we're going to say, how do I do this? We're going to say vector std vector of our vector class, which is a little bit confusing, but that's okay. And we're going to say position, velocity, and acceleration here. Okay, they're all going to be of length 4. Now let me think. Because we kind of know. You want particle n, or yeah, you're right. Let me add an ampersand there, and let me go over here to this file, and let me go down to the very bottom where we have the RK4, and add the particle here. Good. Okay. Now, shoot. Okay. Sorry, I had to check something. Actually, give me just a second. Sorry about having to keep leaving the room. I'll be back in like literally 20 seconds. Sorry, but I know that. Wait, what do you mean? So, why would we want an array instead of a vector here? So, let me think. I guess you're right. We could just use a vector. Doesn't really matter that much. Let's go here. Vec, and let me think. I guess this would have to be of size 4. Is this how you create one? I don't remember. Let me just go ahead and write this. Go here. Ring quit. Make. Yeah, okay. That's probably right. Let's go here. Make this a size 4. And this of size, oops, 1 second, 4. Let's go over here. Make. It's going to give us a warning, unused variable, position, all that kind of jazz. That's okay. So, position, acceleration, good. So these are going to be the RK position, RK velocity, RK acceleration. But that's okay. For now, it's not that big of a deal. What we're going to do is this. We're going to go ahead and populate these guys. So populating the arrays. And let me go over here. 1 second. Array for velocity position. Let's say of size 4. And let's go down here. Populating the arrays. So how are we going to do this? Like I said before, this has to be done kind of sort of recursively. So we're going to basically calculate P1. Or I guess P naught in this case. And so let's go ahead and go through and let's do that. So we're going to say P naught. So P of 0. Position of 0 is going to be equal to particle. And I think it's just going to be dot P. Good. Then we're going to say velocity of 0 is going to be equal to particle dot velocity. And we're going to say acceleration of 0 is going to be equal to particle dot acceleration. Now, the question is, how do we get the acceleration? Well, the acceleration, we're assuming it already has coming into this. By that I mean, let me see. Actually, you know what, guys? Yeah, we're going to have to recalculate a new acceleration every time step. GMM over r squared. Maybe there's a better way to do this whole finding of the acceleration bit. Yeah, we got to think about that. We'll kind of come back to that. But let's keep going from here. Position of 1 is going to be equal to exactly what I said before. So it should be equal to, where are we here? I'm looking down at my notes. Should be equal to x naught, so position of 0. Then we say plus 0.5 times velocity is 0. And then we're going to say 1 second times dt. Now, the thing is we have not read into dt. So we're probably going to have to read that one in. So we're going to say double dt here. And go over here and read in a double dt. Okay, so that's read in. That's read in over here. Now, of course, this means that when we do our force integrate, we're also going to have to read in a double dt. Yeah, I know. I'm trying to think of the best way to do this. I haven't quite figured it out. But we'll figure it out in just a second. dt. What I'd assumed is that we would have a constant acceleration every time step. So what I want to try is, so let me think, what are we missing out on if we have a constant acceleration every time step? Let's just kind of think about this real quick. So let's do page, new page before, page, new page before. Good. So what I've done is I've kind of said that we have, oops, there is something in the way. That's okay. Okay. What I've done is I've kind of said, okay, we calculate all the forces and stuff like that. Based on the position the particle's currently at. If we assume the acceleration is constant for our time step, basically what we've done is we've said, okay, we calculate the forces. Okay, so on, let's say this particle here. So we'll say we have some sort of resulting force vector going in this direction. And this force vector is related to the acceleration. Now, we're going to say for this time step here, this dt, that force is constant. Okay? Isn't it p plus v dt plus 0.5 a dt? Oh, you're talking about the kinematic equation. The kinematic equation is this: x equals x naught plus v naught t plus 1/2 a t squared. That's the equation in a way we're kind of working with. So yeah, it's something like that. Okay, so we'll say that the forces are constant over this dt range. However, in actuality, what we're doing is we're calculating 4 new positions in a way. Here, here, and here. And here, or something like that. No, just there, and there. So we have 4 positions to deal with, which is the original position, and then 4 other positions here. So if we assume some sort of small variance here, then it's not that big of a deal. We can definitely assume that the acceleration is constant. However, I suppose that kind of goes against what we're doing with the acceleration here, right? I mean, like with the Runge-Kutta method. So I suppose maybe we should recalculate the acceleration every time, or every positional step. I went through and checked. Obviously, it's more physical if we don't assume a constant dt. So, or if we don't assume the acceleration is constant over the dt. So let's just go ahead and do it one way. We'll see what happens, see how slow it is, and we'll kind of work from there. Right now, we're not going to parallelize anything. We'll parallelize things when we get to it. Okay, so let's pop up over here. Now let's go down. We read in the dt. Yeah, fine. Let's go up here. I mean, worst that happens, I guess, is we try to speed it up in some ways. So force integrate, we have to read in a dt, which we're going to read in as just 0.1 for now. Go down here, and then we're going to multiply this by dt. Yeah, I've got a feeling it's going to be super slow, actually. I'm not sure exactly how to speed it up, so we're going to have to think about that. Position, let's say velocity of 1 is going to be equal to, let's see, velocity of 0. 1 second. Plus, oh my gosh, come on, where's the freaking plus button? There it is. 0.5 times acceleration. And I'm going to write it like this, but we'll fix it in just a second. Times dt. Okay? And then we'll say, and again, as Guthrum said, because we have to constantly recalculate the acceleration, maybe it's not that big of a deal that we have to change things in this way. So let me just say acceleration of 1 is going to be equal to part dot acceleration. This is for constant acceleration. And we'll modify this in just a second. So we're going to say here, position of 2 is going to be equal to position of 0, position naught, plus 0.5 times velocity of 1 times dt. Okay. Same thing over here. Velocity of 2 is going to be equal to velocity of 0 plus 0.5 times acceleration of 1. Why did I put acceleration of 1? We hadn't calculated acceleration of 1 up there. 1 second. There we go. Times dt. Okay. And then we're going to say acceleration of, what am I going to do here? 2 is going to be equal to, what am I doing? Part dot acceleration. Now, obviously, again, we're going to fix it. Just give me a second. So we're going to say position of 3 is going to be equal to position naught, wherever it was that we started with, plus 0.5 times velocity of 3. Oh, there's no 0.5 in this case. And, oop, my bad. There's no 0.5 in this case. And it is velocity of 2. Then we're going to say times dt. Go down here, position. Yep, that's okay, thank you. Here. Now we're going to say position of, let's say, 3. This is going to be velocity of 3. Gosh darn it, I'm not doing... I can never type. I mean, I always say it's because it's 5 o'clock in the morning, but you'd think at this point that I would be totally used to, you know, just, I don't know, maybe typing or something like that, but I'm not. I can't type. Okay, so now we're going to say acceleration of 3 is going to be equal to part.acceleration. Okay, so now we're going to add it all together down here, and we're going to say position. So particle.position is going to be equal to, and then we're just going to add it all together. So we're going to say position not plus, let's see. It should be dt over 6, so we're going to say dt times 1 over 6. Fine, we'll say over 6. Sure. And then we'll multiply this factor by the appropriate factors times. Then we'll just say what we need to say. So it's going to be velocity. And maybe there's a more efficient way to write this, but this is going to be how we write it for now. Plus 2 times velocity of 1 plus 2 times velocity of 2 plus velocity of 3. Yeah, I know it's 0.6 repeating, but the 0.6 repeating kind of makes it a little bit annoying. So we're going to yank this and paste it. And we're going to change all the positions to velocity. Velocity. Should be okay. So we're going to change this to velocity. And then, of course, we're going to change all the accelerations into these guys right here. And there we go. Now again, there's no reason to keep the particle acceleration. So this is how it would be done if we have a constant acceleration. So we have RK4. So let me just go up and let's just see if this runs with a constant acceleration, and then we're going to go back and we're going to modify it for if we change the acceleration every time step. And we're going to see what happens. So let's go ahead and write this. Go to the top. And what do we have here? RK search. What does RK search return? RK search doesn't return anything, but it does modify the acceleration of our particle. So what we could do is we could change the position of our particle every time step, read it into RK search, and this would create a new acceleration every time step. We'll see what we need to do from there. For now, we have our force integrate function. We have RK4, and we read in particle. We are going through all the particles in root particle vector. So I guess let's just go ahead and write this. Go over here, run quit, run the make command. Okay, everything broke, which is about what's expected. So let's go ahead and fix all the problems. So first of all, we have too many arguments in function force integrate on 44. We shouldn't. So this is an issue with probably the header file, I guess. So let me go into barnshut.h. We go down to the bottom. Where's force integrate? Oh, I apparently just forgot to add a dt here. That was my bad. I thought I did, but apparently I was wrong. You want auto in the RK4 loop? G? I want auto in the RK4 loop. Oh, thanks. There we go. That one would have taken a while to catch. Okay, what's next? Struck particles no member of position. That's fair enough because it is P. So let me see, part P. Where's particle dot position? Let's go to 337. Yeah, I don't usually intend to. I just always forget. I apologize. Now let's try making that. Let me see, vect to double. Got a couple of issues here. Let me see. I set acceleration 2 times acceleration 3. These should both be plus, actually. Down here and down there. Error, no matching operator for star. Operands are vec and vec. That's okay, because we don't need it, but that's fine. So, where's RK4 particle? This should be on 284. Here we are. Change this to particle plus a dt at the end. Now let's go ahead and make that. Okay, that one seemed to run. Now, what does that mean? I'm not really sure. So let's go through and let's output the new position of each particle at every time step in which we do the RK4 force integration. good. All right, let me go up to the top here. Let me just search for main. There we are. Let's go down here. So we have the force integrate here. So this should, in a sense, output change the particle position every time step, right? So what are we going to do? Let's go ahead and go to particle out. Where is particle out? It is there. And what we want to do is continually write to that 1 second. Write to that file every time step. That's what we want to do. So first thing I want to do is change it so that we can write in and out to that file. I think we can with just out. So let's just try it. So let's go ahead and do particle output here, and then do it again afterwards. Particle output there, forcing rate, octree output, particle output. That octree output, oh, yeah, there wasn't, I think you were there when I wrote it. There wasn't very much, there wasn't another way I could think of how to write it, you know? So actually the octree output looks like this. Let me go into, I guess out.dat. I'm pretty sure that's how I did it. It's basically the vertices of every single box. And then we just draw the boxes. Yep. Because that's the only way I could think of how to do it. I mean, again, as I was writing it, I was constantly like, if other people can think of a better way to do it, feel free to do it. But that's how it is. Every once in a while, you know, I never claim to be the most intelligent person on this channel. What I do claim is that I'm up at 5 o'clock in the morning and I'm trying to do programming. So we'll do particle output right before the force integrate function and right after. Let's go ahead and write quit. It's okay. And one thing I want to do is after this particle output, actually let me go into particle output. Here we are there, and there we are there, here we are. And let me just at the very end add in 2 lines. So we're going to say particle output. 1 second, P output. And then I'm going to add in 2 new lines. There we are. Okay, so now let's run make command. And let's check to see what happens. So we're going to see ls. We should have out.dat and pout.dat. vi pout.dat. Oh. Oh, shoot. This was stupid of me. We go to particle output up here. And let's see, force integrate here. Right after here, let's go ahead and add that in. So we're going to do p output. It is exactly what text dumps look. Again, as I was writing it, if you guys can think of a more efficient way to do it, feel free to go ahead. There is no current way, no way that I know of, to draw a line, a single line, without lifting up your pen of a cube. I tried, I couldn't figure out how to do it. I looked it up, no one else seems to have figured out how to do it. You can do a triply nested loop and iterate all vertices of a box. You might not do it in the order you need. Yeah, I mean, right now, new line, 1 second, new line. There we are. Write this, go over here, right quit, make. Then we'll open up pout.dat, scroll down a little bit. Good, 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 good. Look at that, guys. We've changed the positions. You can do a triply nested for loop, iterate over all vertices of a box, but we might not do it in the order that you need. Yeah, so here's the issue. If we do it that way, it's not in the right order. Right, because we have, we'll say, that's just a small piece of code that's supposed to do one thing and then be thrown away eventually. So if we go through all of the, here, let's just go ahead and describe that problem one more time. Let's do page, new page before. Why not? I mean, there's no rush. I mean, as much as I want to get stuff out for my YouTube channel, like, that's really the only thing we're rushing for. So there's no reason to not take our time and discuss things thoroughly. Okay, so here's how we're currently outputting things. We're outputting a box here, and a new box here, and a new box here, right? I mean, yeah, maybe not. But that's how we're currently doing it. I thought of a number of different ways. I couldn't think of it. So I don't know. So we're basically drawing 4 boxes, and that's how it works. The only way I could think of to draw the boxes is to set the vertices that we're drawing in the way that you guys saw. If you guys can think of a better way to do it, again, just... I don't think it's that big of a deal, but let me know. Sorry, I had to put it up. Okay, so this officially output the particle positions, which is exactly what we wanted to see. So, let's put in a time loop. And I guess we can output the Octree stuff every time step too. Not that big of a deal. Actually, wait, the Octree stuff probably won't work every time step. So let's go ahead and right quit, and let's go into new plot. Now what we're going to do is plot, plot, pout.dat. Oh, that was out.dat. We want particle output.dat. Then we're going to say I0. Okay, here's all the particles in their first position. Looks good to me. Now what we want to do is replot. So we're going to go over here, type in rep, and change this to I1. Good. Okay, so one big hitch. All of these guys look to be in the same position. That's a bit of a pain. Could be because our DT is too small. So let's go ahead and update that DT. So we're going to change this to A1. But that library ways to do it has taken time to write. Let's just change this to a 1.0, and let's see if this changes anything. I suppose we could, let me go into new plot, and let's plot I0, I1. Okay, these are also the same position. So this is saying that we're not updating the position at every time step. Happy Little Rat, I have all kinds of nice visualization for everything, but that library ways to do it has taken time to write. Yeah. I mean, visualization always takes a super long time to write, right? I mean, it's not trivial. You know, and it frustrates a lot of physicists because like they do the science and then they have to prove that their science is correct. And, you know, visualization is one good way to do that, but at the same time, it's a pain. So, okay. So what's the issue here? The issue here is we didn't update anything. Yeah, so let me see. Yeah, maybe it's G. Maybe that's the issue. Yeah, that actually might be the issue. Because it's times 10 to the negative 32nd. Plot 0, plot 1. Okay. I thought maybe just increasing the time step by an arbitrary number of zeros would help. Let's try it again by changing the gravitational constant. If you can visualize your work, it's always worth it. Also makes much more readable papers. It depends, right? So sometimes there is a number of visualization that looks stunning, but you know, you don't want your paper to be clickbait. You know, that's the last thing you want your paper to be. So you don't want it to be that people look at the image and they're like, oh, that looks so pretty, and then they're disappointed when they go into the article, you know? That said, yeah. Okay, so let's go down to our force integrate function. And see what we got here. So node root should be okay. Maybe the particle significant mass. Yes, so let's go ahead and check out some things. First of all, when we initialize all the particles, let me go up to here, vector pvec, where are we? Create random distribution. That's probably what we want to go to, create random distribution here. And one thing I failed to do when we create all of these guys, I failed to go through and give these guys, let me see. We gave them, let me see. Velocity, we need to give them velocity and acceleration. So let me go ahead and update. One second, let me update something. I don't know what I'm looking for. Every once in a while, I'm just in the middle of coding, and then I just completely lose everything. Okay, here it is, velocity acceleration. What do we want? We want mass, particle. Here, explicit particle, p double mass. We also want vec. And I want velocity and vec acceleration. Okay, now we say pp, mass m. These are in the wrong order, so let me put them in the right order then. So we'll go ahead and update them with velocity and acceleration. 1 second. The particle mass is 1, which is quite large when compared to g, which is 6.67. So let's go here and let's say vec v and vec a. And let's go here and change this so that they are appropriate. So oh, that wasn't what I wanted. Yank the whole line, paste the whole line. Delete this, X there. Okay, so now we're gonna say vec velocity there, so let's do it. So we're gonna say velocity of v, and of course acceleration of a. No, you need larger mass to cancel out the e to the negative 11th. Yeah, wait, I'm thinking. Let me go ahead and, yeah, you're right. So let's go here, and let's add in the appropriate vectors. In this case, we're gonna set them both to 0, but it's nice to have vec here. And this should initialize them all to 0, if I remember how we initialize vectors. So that should be okay. Okay, just making sure we have them. Good. Good, that looks good to me. So we'll increase the particle mass to something obscenely large. Let's just do e to the 20. Okay, now we're gonna do make one more time. Let me go ahead over here and write. Make sure nothing's broken. I've got a feeling there is something here that is broken. Barnes Hut H60.22. PVA. Telepathy, thanks man. So let me see, what do we have here? 60.H57. No matching call for particle vec double. Okay, fair enough. So let's go up to, what do we have here? Barnes Hut.H, and we want to go to 57. And let me check something. Vec PVA velocity. I think I did it right. Let me see. Alright, Twitch, thanks so much for coming in, man. I do appreciate it. Watch if they all end up in the center. That's actually what I'm hoping for. If they all have some sort of forces that are acting on each other, we have the force integration down. I've just got a feeling it's broken. But yeah, thanks for coming in. I love Twitch. Okay, so I think this is right. Velocity V, acceleration A. Oh, is it supposed to be the other way around? Oh. Oh, wait. Mass M. One second. You put them all at 0, 0, 0. Yes, I wanted them all to be at 0, 0, 0. Why would I not want them to be at 0, 0, 0? 1 second. In the initialization, you put PVA, VAP. Vec P, Vec V, Vec A. It looks right to me. Let me just go to 57 and fix up that one. Here. So it should be center mass. We're gonna say vec. Vec. One second. Of course, I could just be missing it. And then we go to 60, which is another issue here. So we're gonna say vec. Vec. Okay. Then we go up to the top and let me see if we can figure out what the issue is there. So Gusman says we did PVA. I did VAP. Let me see. Particle velocity acceleration. VAP. PAV. Oh, you're right. I totally see what you mean now. You were totally right. Okay. Sorry about that. These guys need to go down here. Yep, I got you. That was my bad. Again, don't claim to be an intelligent person. No, you're good. I just didn't understand. You're set. Okay, this should be okay. Let me just go ahead and delete this. Go down here and change this to particle mass. Done. Okay. I thought you were talking about this over here. You were talking about this over here. Good. So let me go ahead and write this. Go over here, write and quit. Run make one more time. This one seemed to make okay. Now let's run new plot one more time. Let's run P0, P1. Still the same location. And let me actually just go into the file itself. So Control D, vi pout.dat. It's all times 10 to the negative 21st. What? Why is the box length? Sorry, Zadison. Yeah. I'm sorry. It's particle output. Okay, what do we have here? Okay. So somehow or another, these guys are super small. Let me try something. Right, quit. Let me go into barnshut.h, and let me see if somehow the particle mass is influencing this. So let me change this back to 1. Right, quit. And let's go into make one more time. Then I want to go into pout.dat. Yeah, so somehow or another, and I'm not sure exactly why, the particle mass, 3.82, is affecting this. Yeah, and I'm not, that is weird. So let's go through and let's check this. Particle mass. Where have we done anything with the mass? So let's see. Particle positions will be changed in create random distribution here. So let's see, we have vec box distribution gen. How do we generate box distribution? Nothing to do with mass so far as I'm aware. Yep, so we're initializing them all with a position. There has to be a pouting Twitch icon. You know, there is one thing. What I decided, if we ever did get Twitch emotes, I have to create like one that says boring or something like that, and it's Niels Bohr, or you know, something like that. Like also LaTeX symbols. I would love to see LaTeX symbols in chat. Okay, what do we see here? Vec box distribution generator. Vec particle mass. Should be fine. It looks okay to me. Why would they be influencing each other? Let me go to particle output. Where are we? Particle output. A second. Out. Here we are, particle output. What are we outputting? We're outputting position X, Y, and Z. If current pvec.size equals 1. I'm using Arch Linux with OpenBox Windows Manager and Sakura terminals. Okay, I have it set so that I can automatically tile it by, like if I open up a terminal, pressing L or H. So tiles that way, tiles that way. So, okay, what do we do here? Recursively outputting additional particles. Particle output. I did. Let me just search for all autos, make sure I didn't do that again. Sure did. New. Okay, so I think I hit all of them now. Let's write this. Just write it. Go over here. Make it one more time. Okay, so this. Oh my gosh. Auto 7. Thanks, Gustorn. Okay, now let's go into pout.dat. And let's just plot them. So let's go to, where's the last new plot? Plot 0. Plot 1. Yeah, okay, that doesn't really help any. Okay. Control D. Now, we have to figure out the issue with why is the particle mass influencing the particle positions? Okay, so let's think about that. Why would the particle mass be influencing the particle positions? Well, let's go up to main. Okay, here we are in main. Let's see, we have particle output. So what did we do? We did depth for search, divide octree. Depth for search does seem to touch root, but it shouldn't bother it that much. So let's go here, comment that out. Pvec is equal to create random distribution, and we do divide octree, root new node. Wait, let me think. Do we ever give root pvec? We might not. So we have that. Particle output, root. Yeah, but it shouldn't be doing what it's currently doing. Okay, one thing I just noticed, let's go to divide octree, And let me see what we got here. Okay, divide octree. We are reading in pvec here. So let me see, auto child, ampersand. Let me see. Make octree current. Auto child current children for auto p and pvec. Okay. So else child divide octree child pvec. Do we ever come? 1 second. For auto p in. Okay, so for all the children. 1 second. I have to think about this. For all of the children, we go through and we say auto p in pvec. However, let me think here. How does this work? So we're iterating through all the children. We say auto child and current children. And then we decide the number of particles in the current box, which is fair enough. So we read in pvec. That should be good. Then we go through here. We say child pvec pushback. Good. One thing I failed to do, guys, is I failed to do this. So let me go up to main and let me do one quick thing to check something out. So we're going to do the following. We're going to say root dot pvec is going to be equal to pvec. And I think this needs to be an arrow. Not that this should really do anything, but let's just see what happens. Make it, we get a segmentation fault. That's a little bit different. Okay. So, let's see what happens. Where's the seg fault coming in? No idea. So let's do this then. Let's go ahead and remove star.dat. Now let's do make again. Let me ls real quick. We do have 2 output files. Right, this. Let's try it again. Make. Force integrate. So let's not do this one. I bet you it's in the force integrate file function. So let's go ahead again, remove those guys. Make. Dagnabbit. Make that. Let me ls. Okay, never mind, I was wrong. I have to think. Let's go ahead and dd here. Over here, remove that. Okay, so I don't know where the seg fault's coming in at. One thing I noticed is I forgot to close p output, but I don't think that's where the seg fault is coming in. We can check, I guess, but I'm fairly confident that's not where it's coming in. Okay. Particle output there. Output.close. Oh, yeah, let's make. Yeah, so it works without force integrate. Okay, so now let's go down to force integrate and let's see what's happening there. So force integrate here. Okay. So we're going through auto ampersand part in all of the root p vector, and we're doing an RK search. Okay. Then we're going to go through all the root p vector one more time, and it should be that auto part root. That seems right to me. We do RK4 of particle and that. So let's go through RK search. Let me see. Actually, you know what? Let's just go through here and let's output. std cout I end line I equals 0 and I plus plus. I know this is stupid, but just want to check something. Make int make 0. Okay, so we break at the very start here of the RK search function. We might, so let's go down to RK search. Yeah, I mean, you're probably right. So what are we doing here? We have a current particle. So let's go ahead and remove this. We know that we're breaking an RK search. Okay, so what do we have here? We are reading in a current node that we're working with, starting with root and then going from there. We say vector D is going to be, yep, that should be fine. We worked on this yesterday, so maybe we remember it, maybe we don't. So vector D is equal current P minus particle P, okay, inverse R. And then there should be the issue. The issue is probably down here when we do our current children guide down here. So we say for auto child in current children, we do an RK search, reading in some sort of particle that we're going to be working with, and then the child of that particle. Okay? Show, let's see. It would. I'm sorry, I just need to think about it. Gustron says, oh yeah. So maybe he knows what's going on here. So let's say for auto child, if, oh, yeah, 1 second. Yeah, let's grab this guy and let's put it down here. Now let's go here, make. Oh, write it, make. Okay. So we still get the segmentation fault. Let me see. Let's check to see if we get any further. I don't think we do. Sorry about that. I equals 0. Then we're going to do std cout I and line. And I plus plus. Make. Okay, so we get to 99. How many particles are we supposed to have? I think 100. So I think that's about right. Okay, so it looks like we go through all of them. Let's do the same thing here. Int I, oh, I guess I equals 0. Then we say std cout I and line. And we're going to say I plus plus. My bad. Let's do it again. Make. Okay, so now it breaks on the RK4 loop. I guess we can put a new line just to make sure. std cout. 1 second. New line. New line. Make. Yeah, it totally breaks in the RK4 loop. Okay, so let's go to RK4. Down the bottom. Okay. So going through all the particles. Each individual particle, we have a dt that we're reading in. We have vec, position 4, velocity 4, acceleration 4. Unless I initialize those guys wrong, which I suppose maybe I did, that should be okay. This all just looks like a bunch of math to me, so I'm not seeing where the issue would be here, unless I'm calling something that shouldn't be called. So let's do position 0, good. 0, 1, 0, 2. Good. 0, 1, 2, 3. Let me go back up real quick. So what do we have here? RK4 part dt for part in root pvec. Yep, that's definitely going through all the particles. So let's just remove RK4 real quick. Make. Okay, good, just checking. I mean, obviously, I suppose that was fair enough. Okay, so let's just do this then. Okay. So let's do std cout. And yeah, I realized a debugger would help here. std cout. 4 found. Up here, std cout. 3 found. One second. cd cout. 2 found. 1 found. 1 second. 1 found. Oh, my bad. And then up here we're going to say not using YY. What does YY do again? Wait, Y yanks. It should be fine. Yeah, I mean, we yank the full line and then paste, right? But it's okay. Let's do std cout. Starting. Okay, let's go here, write this. Make. Semicolon. Make. Starting. Okay, 1 found. Break at 2. Yeah, I see that. Okay, let me see. So we broke at 1. So let's see. Position 0 plus 0.5 times velocity 0 times dt. So let's go up here and let's output what we need. So we're going to output position, velocity, and acceleration of each of those guys. So let's do position 0, tab, velocity 0, tab, and acceleration of 0. Right here, go over here to make. Vec is not derived. Oh, oops. It's got a .x.y.z. So let's .x for all of these guys. .x. .x. Make. So the velocity is 0. Acceleration, everything else seems okay. So let me see. It obviously doesn't go any further than this. So let's, I guess, just check y and z. The velocity should still be 0 at every point because, well, it started at 0, and that should be okay. Make. Yeah. Z. Make. Yeah, I didn't figure that'd be an issue. Okay, so we have the position, velocity, everything else should be set. I think I see the problem now. So we're gonna do this. 0.5 times dt. What if we do 0.5 times dt times velocity? That's 2 times. It really shouldn't make that much of a difference, but I don't know, let's see what happens. Let's go to make. Nope, didn't do anything. I thought maybe. Okay. Yeah, sure, sounds good. vec.h. Okay, so in vec.h, what do we have here? We have position equals, what am I looking for? We have plus, times, and velocity there. So what do we have here? We have vector operator minus. Okay, vector operator plus. Yep, so you're just left-hand side, right-hand side, that should be okay. Times, let's see, left-hand side, right-hand side. Double vec. Vec double. Are they tab inted? Oh, down here? Oh, I don't know. It's fine. They actually aren't tab intended. I can remove them if it bothers you. Oh, that one is. Um, 8x? Sure, whatever. Doesn't matter that much. Okay, print vector v. Inline distance. Okay, that's not a matter. Let's go up here. Double dot. Vector left-hand side, right-hand side. Vector cross. Sounds good. Vector operator divided. Not using that. Vector. You have a double B. Let me go up. Let me see. Is there a double left-hand side vector right-hand side? Yep. Oh wait, maybe this is the issue. Let's change this to return vector of left-hand side dot x. Oh, that's the double. So right-hand side dot x. Left-hand side times right-hand side dot y, and left-hand side times right-hand side dot z. Okay, let's go ahead and right quit. Make that. Okay, good. So this one seems to run. Thanks, Gustorn. You can just do right-hand side times left-hand side. Let me see. Yeah, oh, this one seems to run. Okay, so let's go ahead and remove these lines. Well, infinite recursion was right. Go here, dd, 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 dd. Okay, let's write that. Go over here. Let's make this. Okay, so we are going through all the particles. Let's go ahead and remove the printing out that we did for debugging. Again, I really need to learn how to do a debugger, but honestly, the full year that I've been here on Twitch, I have been saying that, and guess what I haven't done yet? You know, one day, I'm just gonna sit down and we're just gonna learn a debugger together. Write this, go over here, make that. All right, let's check the particle positions. Vi pouch dot dot. Okay, so we start there, we end, well, in the exact same positions, I imagine, because the change is so small. So let's go up to the top. Now we've got one more mystery to solve. Let's go over here to Barnes hut.h, and let's change the particle mass to, again, something really, really large. So we're going to say 1e to the 20th. Quit, make. Now let's check pout.dat. Again, the thing that bothers me is somehow now they are times 10 to the negative 21st. So let's check that one out. Why would they be of, like, you see what I'm saying? So I changed the particle mass, I think, didn't I? We go into barneshut.h. Yeah, I changed the particle mass, and now all of their locations are times 10 to the negative 21st in size. Yeah, but this is scientific notation. So 1e to the 20. That should be right. Let me see. CD, C out, 1e20, new line. Make, 1. One second. Make. Yeah, that's 1,000. 1e to the 3 is 1,000. Sorry. You had me worried there for a second. Okay. DD. Good. Okay, they're all being pulled to the center of mass, which, given the distribution, is probably close to 0. I would say that could be true. The only issue with this is that that very first output is before any of the force integration. So that's just the initial locations we're giving them, which means the initial location is not correct. Yeah, that initial is not correct. So let me go down to the create random distribution again. Here we are there. There we are there. I was in the right function. I don't know what I was thinking. Okay, so real box distribution, box length. What's box length defined by? Pretty sure, but what we can do just to make sure is we can go down here and we can do the following. We can say, oh, actually, let's just do this. Write this, go over here, and make that. Okay, so, oh, shoot, maybe you're right. Dang it. Yeah. Okay, I was wrong, you're right. Shoot. Well, then what would the issue be? Because this is... Okay, so here's what we did. We created a random distribution. Okay. We set the root position vector to be the position vector that we just created. We then do divide octree. We create the files, And then before doing anything at all, we output this. Okay. I just use one seed for testing to have the same numbers between runs. But the issue isn't that they have the same number between runs. You're overwriting it? Let me see. Where am I overwriting it? Rather appending to it. Later I am, yeah. But not right here. So like, for example, if I remove the second output, let's go ahead and remove the second output. Let's go here, right quit. Oh, sorry. Make. Now let's go into, maybe you're right, maybe we are. In which case you're, no, still times 10 to the negative 21st. Okay, let's write it again just to be sure. Right quit, remove star.dat. Let's run it again. Make, open up the new file. Yeah, okay, times 10 to the negative 21st. So this, to me, is rather weird. Particle output, we output root and, okay, so let's modify how we're doing this then. Let's go ahead and quit here. Let's grab these guys up here, put them at the top of main. Remove these two lines here. Remove a couple lines down here. What's in particle output? Particle output, let's go to that. I checked that just a second ago, but maybe I missed something. Particle out here, particle out there. Okay, so if we are not in the current node, what we're going to do is we're going to go through. We're going to say current pvec.size equals 1. Okay, so we're going through and basically we're outputting all of the leaf nodes, right? So we recursively go through all of the nodes in our octree. And as we go through all the nodes in the octree, if there is a particle in our final node, so if there's only one particle, if we're in the final box, we do the outputting. Then we say for auto child in all the current children, so that's going to be 8 of the current children, we do particle output again. So we just keep going until we get to the last one. Did I initialize center of mass? I mean, here's the thing. It must be initialized for a number of different reasons. But we can check that, find center of mass here. Center of mass, let me see. Where are we? Where is find center of mass? We should be doing it in divide octree. Hey, by satellite, what's up? So we're gonna say make octree current. So we divide it into 8 subnodes. Then we say iterating through all the children. We're gonna say auto child and current children. Now one way I know that we are initializing center of mass is here. We say current center mass. However, now I finally realized the issue. Zadiston, you're right. What we're doing is we're outputting the center of mass. We're not outputting the position. Yep. Okay. That's fair enough. So what are we doing? Child composition. Yeah. So what do we have here? Child center mass dot mass should be correct. Yep. Okay. This is fine. So what we're doing here is we're going through all of the particles. Yeah, so we're going through all the particles. We are adding all the positions together. 1 second. Child position. Center mass. 1 second. Let me think. We have to find the center mass, right? So the idea here, but there is something wrong here. There's definitely something wrong here. And I'm trying to figure out exactly what the issue is. So let me think. To find the center mass, it shouldn't be com.p. It should be a sum of all of the particle positions. So we add all the particle positions together. Then we divide it by... Yes, that's exactly what I'm doing. I'm missing the multiplication by mass. Now, I think this can be solved simply by going up here and saying we multiply this. Oh, my bad. 1 second. Times p dot mass. Now, this means that the com dot position is not quite right, which is a pain. But let's just see if this fixes the one issue. So let's go ahead and right here. Go over here, let's make that. Go into pout.dat. Okay, so this fixes one of the issues we've run into. G. Okay. However, this means that the center of mass does not have appropriate positions. No, it does. It does. It does. It does. We're set. Center of mass has to have appropriate positions. We're set. This is good. This is good. Thanks, Addiston. Okay, so let's go ahead and write and quit here. I don't know why I wrote and quit in a data file, but that's okay. Let's go up to main. Main, up here. Okay, let's add in the particle output here, and let's see if the particle output changes any. So let's go to make. Now we're going to do last new plot, which should just be, well, new plot. Plot the first and plot the second. Dagnabbit. Okay, these guys are still in the same location. Exact same location. So let's see, maybe it's because they're too far apart. So let me go into barnshut.cpp. I changed the particle mass to be super high. Let me see how we're doing everything down here. So particle P, particle acceleration. Let me see how we're doing this guy. So particle acceleration is going to be d times g. Let's just output the acceleration every time step. Let's just see what values we're working with here. Let's do particle, SED, cout, particle, dot acceleration, new line. Right here, go here and let's control D and make. We are dealing with, I think there's a print. I think. We'll see what happens. Make. Okay, well that's something. Okay, lots of accelerations there. Yep, yeah, it's a lot of numbers. Yep. That's a good number of numbers. Okay, let's just look at the order of magnitude here. We have 4 times 10 to the 9. Hey, Flight from Nowhere, what's up? Make. Bah. Too many arguments to function void print. Yes, what is the question? Feel free to ask. In the function. Oh, obviously, sorry about that. Let me go into vi-vec.h. Go down to the end here. Print f. Then we want a new line. Make. There we go. Good. I would rather not answer that question. Deeply personal, but I don't know. I don't really do that kind of stuff, honestly, and it's really weird, and I just don't really like talking about it. But thanks for the question. Again, I mean, the thing is, especially in Japan, I'm like terrified because I know that they're super, their copyright stuff is super heavy over here. So like you can go to jail if you accidentally click on the wrong link or something. So I kind of definitely avoid it in Japan. But sorry about that. I don't know. I was raised incredibly religious, and that kind of stuff was kind of frowned upon. So I never really built a habit when I was younger. So it's not something that I do very frequently. Sorry about that. Okay. So particle acceleration. The accelerations are incredibly high, which means you would think the position and velocity and everything else is also pretty high. So let's see. We do the RK search. It could be that we're not appropriately updating the positions of the particle. Yeah. So let me go through and let me check something then. We have apparently been updating the particle accelerations, right? However, for some reason, it doesn't seem to keep going. Okay, so let's see. Maybe I misspoke, but no, I don't typically, I guess, indulge in that side of my my, I don't know. So let's say we are changing root here. We have all the particles. 1 second, I have to think here. We have a particle vector. So let's do this. For auto particle in root p vector. So that means we're going through all the particles. Let's do this. Let's do print. Afterwards, what is the problem? Particle dot acceleration. Make. Okay, so particle acceleration is totally being updated. Let's think. Okay. Not sure. Let's do this. Gustron says he knows what the problem is. We'll see what the problem is then. Your octree should be storing particles, pointing to some global vector of particles. Your octree should be storing particle star. Let me think. So let me go to see what we're doing with the octree. So let's go to vi barns hut dot h is what I need. And let's see, what do we have here? Particle is here, struct node is there, and we have particle center of mass. And what you want to do is you want to say, instead of vec position, actually should be storing particle stars. So what you want is vector of particle stars. Why? What does that do for us? But now that I think about it, this should still work if you don't leave out any ampersands. Maybe we did. Let's go down to RK search. The particle is being updated. Hey, let's do it this way. Let's do 4. Exactly the same loop we had before. Let's just output it to make sure that we have the, let's do print. And what do we want? We want particle dot acceleration. Let's go over here, right quit, and let's do make. Okay, so the particle accelerations are totally being updated. Just to be even, doubly sure, let's go through here. And let's go down here to the RK4. And every time we get to here, let's output particle acceleration again, just to make sure that we are updating everything. So let's go here, and let's do print particle dot acceleration. Go over here, make. Yeah, the particle accelerations are totally being updated. Okay, so what do we have here? The acceleration 1. Check RK4. That is currently what we're doing. So dd part.p part.velocity part.acceleration. One second. I just realized something. If the first velocity is 0, okay. Show the loop calling RK4 again. Sure, it's up here. It's just auto particle, and we're going through and calling RK4 for everything. It's constant all 4 times. It is constant for all 4. That was one thing that we mentioned. Now let me think. Is that an issue? Well, let's say we have a constant acceleration due to gravity, just like being pulling down to the Earth, 9.81 meters per second squared. Okay. So let me go back down to that. Sorry about that, Gustron. I can't show them both on screen. Oh, maybe I can. I can just barely show them both on screen at the same time. Maybe if I go down one more. No, okay, good. They're both on screen, same time. Okay, so what do we have here? It's assumed that all particles have already updated their acceleration. That seems fine. Okay, so acceleration 0. It's particle acceleration, whatever. Position 0 is going to be 0.5 times dt. Velocity 0, okay? Velocity 0, good. Velocity 1 is going to be times... You need the pointers? Wait, why do I need the pointers? Sorry about that, I'm not... Why would I need the pointers for this? Let me see. So we have particle.p. It's not obvious to me why it won't work, is what I'm saying. Because it seems to me like this should still be fine. See. You're updating the particles in root and printing the ones in the leaves. Oh, yeah. Yeah, you're right. Yeah, you're right. Okay, that's fair enough. Okay, so let's go into VI. What do I want here? I want Barnes Hut dot H. Yeah, you're totally right about that one. Okay, so what do we have here? Let's see. So we want a vector of particles pvec. Let me think. All right, this is gonna take some time to figure out. So I need them all pointing to the same. Yeah. Yeah. We should probably fix it this way though. So let's see, STD vector of particles. What we actually need then is not a vector of particles in every node. We need... Would that work? Just particle star? I mean, we can check. I guess we'll just run it with particle star. It'll break everything, I think. Yeah, obviously everything's broken. But let's see. So let's go to 33. Your version on GitHub? Oh shoot, I never went through and checked that up. Sorry about that. I kind of ran out of time and then I didn't think about it over the weekend. No matching operator for equals. Let's see, so we changed the particle vector. Okay. If you wouldn't mind, could you link that again? Sorry about that. Okay, so we have no match for operator equals. Operator types are vector, particle, and vector. Okay, so let's see. What we need to do is go up here and change this to a particle star. Let me just clear. And let's check this. Make. Okay, so it says create random distribution. Obviously, I'm gonna have to update everything here. So let's see. Create particle, non-scalar, create random distribution. Let me think. So let's go into Barnes Hut .h. Okay. 1 second. Open link. Good. So let's go through here. Let me see. So it should be under Barnes Hut. Barnes Hut.cpp probably. Okay, what do we have here? Where is the... Yes, so particle star, node star. Okay, so let me see. Where is create random distribution? Auto particles. Fair enough. So where do we put create random distribution? It's still a vector of particles. Then we say auto root new node particles. So what you did is in node, you say vector position. 1 second. Initial particles. Here, this is the guy I want. So let's go over here and let's check. So what we'll do, STD vector create random distribution should be fine. So I guess you leave that as that. And now let me check my, there's even a comment in main. Node here, p vector. Let me see, where's main? Main is down here. First allocate the list of particles. This will not be copied, only pointers will be used. Make sure not to use a free vector while Octree has references to it. Yeah. Okay, so let me go through, let me just kind of manipulate what we have so far. Unfortunately, it's about 6:50 in the morning, so there are some things that I probably won't be able to get done. So here's what I'm gonna do. For now, let me just go through and let me do this. So I'm going to do this in a very crappy way, just to make sure we have all the positions being updated. 1 second, let me think. I have to go over here, change all these back to just particles. And then we'll worry about adding the particle star stuff in tomorrow. I just want to make sure the RK4 stuff is working in the current iteration, and then we'll go from there. So let me go ahead and make this. Good, looks fine to me. So now what are we going to do? We're going to output the new particle positions. So let's do here. Let's say std cout. You guys are going to hate this. Part.p.x, part.p, dot y. Of course, tab. I missed a tab last time. Tab part dot b dot z. New line. Let me add a tab over here. Totally forgot about your stream on last Sunday. No, don't worry about it. I actually missed the stream last Sunday, I think. Oh, well, yesterday. I did stream yesterday. Okay. So now let me go up to the top here. Where are we? We are root, pvec, p output, and n. That's fine. What I want to do is the following. I want to say for auto particle in, let's see, where are we? pvec. std, cout, p art dot x. Pretend I can do this right. Part dot p dot y. New tab. Part thanks dot p dot z. New line. Add an ampersand in here. Write this. Good. So now we're going to output two new lines. std, cout, new line, right over here, go over here, vi make file, and what do we need to do? Make. One second, adding a scene there, right here. Make. Okay, let me check particle. Check dot dat g. Okay, well they clearly changed in position. You're gonna love this. So let's go into new plot. Let's go into splot I0. Here they are all initially neatly packed between 0.5 and 0.5, and here they are at the end. 1 second. Why did that? Oh, that's because they're wrong. Let me change this to particle. Check dot dat I0. So this is where they are, again, all neatly packed between 0.5 and 5. Now let's do a replot here. Replot here. Change this to I1. And here they are all neatly packed between -1 times 10 to the 12th and here. One thing I don't like is that they're all confined to a plane. That's something I need to think about. Under what situation would they all be confined? But the plane is kind of weird, right? I mean, it's like... Maybe this is right. I'm not sure. We'll have to think about that one. So what do I need to do here? I'm going to write some notes for tomorrow real quick. So here's what we need to do. We may be ignoring particles. Okay. Let's say adding some more notes in. We've already implemented theta, so we can remove that node here. And let's add something in over here. So we're going to say all particles drift to a plane. And let's add in another node up here saying change particle vectors to particle 1 second stars. Okay, so yeah, please go ahead if you want, and then I'll just go ahead and accept that. And then that'll kind of help us move along. Basically, guys, the faster we get through this, the faster we move on to OpenGL, which is going to be basically banging my head against a wall. So we'll see how far we get there. One thing I want to do real quick is I want to change the time step of force integrate to 0.1 and change the masses of the particles to be a little bit smaller. Let's change this to 0.1. 1 second. 1. Right quit. Vi Barnes Hut. Dot H. Times 10 to the 20 is quite large. Let's drop that times 10 to the 10. Let's go over here. Control D. Make that. Now let's go ahead and do the same thing we just did with the new plot. Actually, let's just check down here. They don't seem to move that much. So let's see what happens if we do new plot. And we want to do plot the initial positions and then replot their changed positions. Okay, now that's a little weird to me. Let's go ahead and control D here. Let me open up particles, check.dat again. The weird thing... Oh. Oh. Some of them are still quite high. Let's remove particle check.dat. Let's make it again. Make clean. Make. And now let's check the... Make... let me just run it. Barnes Hut. There we go. Okay. Let me see. If we... 1 second. Let me open up the file. Particles check.dat. Let's just scroll up. See, that one looks okay to me. Okay, so let's do this. Let's do Barnes Hut particle check.dat. There we go. Now let's run a new plot. Sorry about that. That was really hard to follow. Now we're going to do replot. Okay, so here we see the particles clearly changing position, which is good. Zadison, what did you just realize? This is September 21st. My Twitch account turns 2 years old. Fantastic. Okay, so again, they still do that weird plane thing, and I'm not sure exactly how physical that is. I've got a feeling there's something wrong here. So let me take a look at what we have in the barneshut.cpp file down here. Your particles will accelerate towards the center of mass and fly off in space because gravity isn't likely to pull them back together again. Yeah, there is a particular balance of forces that we have to figure out here, and I'm not sure the best way to do that. But we'll kind of hit that as we hit it. I think we'll hit it probably tomorrow. First thing we have to hit tomorrow is changing all the particle vectors into particle star vectors, which, you know, Gustorn has already basically done in his code. And it's kind of small updates, but it's stuff that needs to be done. And I need to kind of think about how we need to fix that. Force integration stuff, we have to take a look to see how physical the system is. Is it correct to say that all of them are kind of going into a central plane? I don't feel like that's right. Then what do we need to do next? We need to, let me see. We may have to ignore the particles that are too far away. Yeah, that's another thing we might have to consider. So I think, was it not you, Zadison, that brought this up? That said we may have to consider or ignore particles that are too far away. Someone mentioned that yesterday, and that's kind of coming into your point. Okay, so let me go ahead and check the force integration scheme one more time. Force integration. Oh, misspelled force. Integrate, not integration. Sorry about that. We do an arcade search, change all the appropriate accelerations from there. Now, why? Hey, Linux. Or James. I must say, I'm loving your stream. Thanks, man. I appreciate it. Okay. So, let me see. Current position, particle P. Man, I have no idea why they'd be confined to a plane if it's not a physical thing. So let me see if we can catch it drifting. So let me go up to the top. Let me change this time step to 0.01, one order of magnitude smaller. Right, this, go over here, Control D, and let's run the make command. Okay, now let's do Alaska new plot. Plot here, and then plot it one more time there. Okay, so here we actually see the particles drifting. That's kind of neat. Let's drop it one more order of magnitude. Why would they all... Is it the same plane every time? Fled from nowhere, you're also... James? To be fair, in my previous university, let me see. In my previous university, there were, 30 or 40 physics majors? And of the 30 or 40 physics majors, most of them, the most common name was James. So just pointing that out, James is a very common name, at least in the US. However, here at OIST, I don't think I've met another James. I think I'm the only one, which is kind of neat. I'm not liking that whole line thing. Let's check the slope of that line. It goes from negative 0.2 to positive 0.2, negative 0.2 to positive 0.2. Okay, let's check it again. Did you typo a coordinate? I might have. That's something I need to look into. But we will leave that for tomorrow. This will be a cliffhanger for the next day. Here's what I'm going to do. I'm going to go ahead, right, and put this. I'm going to run a get status. Dot. Because, let me see. Because Gustorn said he might like the code, I'm going to go ahead and commit this to GitHub. So let's go ahead and do git add barnshut.h. Let me run a git diff on the makefile. What did we add in? We added in barnshut.h, fair enough. So now let's run git add the makefile, barnshut.cpp, and of course vector.h. Good, let's run another git status. Dot. Modified, good, everything's modified, so let's do git commit. Ignore all of these files, my apologies guys, and we will say adding in skeleton for RK4 force integration. Let's say we need to modify one second, into your operator star. One second, operator star. We'll take a look at it. Okay, so we need to modify particles to particle star. One second, particle vectors. S to particle star vectors. Good. So I'm gonna run quit, git push, origin master. One second, I don't think it's a problem with vector.h. I think vector.h is probably fine, but we can take a look at that later. Again, Gustrun, I really appreciate all the help, but you don't necessarily need to if you don't want to. Again, I always say this, like, I know you guys are super helpful, especially Gustrun, Zadiston, people who have been helping me with the stream here. You guys are absolutely super helpful, and I love having you guys work with me while we're doing this, but at the same time, it's not expected. So please don't feel like you're obligated to do anything. We can figure it out together on stream tomorrow, but if you want to, feel free to submit a pull request tonight, if that's what you want to do. Okay. Yeah, if you don't have time, you don't have time. We'll work on it tomorrow. For now, we'll leave it as a bit of cliffhanger for tomorrow. At this point, we've pretty much done, well, a bunch of stuff. We've implemented an RK4 algorithm. We need to test to see if it's physically correct. We have implemented an octree code. Again, we have to modify this a little bit, but we're getting there. I say one more day probably of start coding, and then we move on to the OpenGL stuff, which is going to be more coding, but at the same time, we'll kind of get there when we get there. Again, I'm pretty excited to work on this tomorrow, so we'll see how far we get. And then it's just a matter of checking how physical our system is. That's it for today, guys. Have a great day, night, afternoon, morning, evening, whatever time it happens to be your time. And I will see you around next time for the next episode of Simuleos, where hopefully we resolve some of these issues and we move on from there. Thanks, guys, so much for coming in. See you around. Bye, guys.